Here's a sample exam 6 of the Prob and Stat actuarial exam. Problem number 1, suppose a box contains 4 blue, 5 white, 6 red, and 7 green balls. In how many of all possible samples of size 5 chosen without replacement will every color be represented? Sample exam 6, question 1. Here, we're going to use the multiplication or the rule of the product in counting, which says, if you have 2 pants and 3 shirts, how many combinations can you have? It's 2 times 3. And so this is the same principle. Sometimes it's called a hypergeometric or multivariate hypergeometric. We have 4 blue, 5 white, 6 red, and 7 green. And we want at least 1 from each color. So the possibilities are that we have 2 reds and 1 of each, and then 2 whites and then 1 of each, 2 reds and 1 of each, and 2 greens. And then this is 4. How many ways can you choose 2 from the reds? It's 4 choose 2, 5 choose 1. And then you do that for each of the possibilities, and you come up with this, and then that's your answer. Number 2, let x and y be bivariate normal distributions. The mean of x is 10 and the variance of x is 12. The mean of y is -5 and the variance of y is 5. The covariance of x and y is 4. Then what is the probability of x plus y being greater than 10? Question number 2, we're asked to find the probability that x plus y is greater than 10. But first, since we know that x and y have a bivariate normal density, then the sum is also normal. And then we have to find the mean and the variance of this distribution. And so if we look at the mean, it's 5, and the variance, bless me. The variance is the variance of x plus variance of y plus 2 times the covariance, and each of these are given, and that's 25. So x plus y is normal with a mean of 5 and variance 25. So now if we subtract the mean and divide by this, the variance associated with this, it's actually divided by the standard deviation, then that transforms to a z distribution, standard normal. So the 10 minus the mean divided by the standard deviation, the square root of 25, which is probability of being greater than 1, which is 0.16. Number 3, let x and y have joint probability distribution function f of x is equal to 5/16 times x times y squared, where x is between 0 and y is between x and 2, and 0 elsewhere. What is the marginal density function of x when x is between 0 and 2? Problem number 3, we want to find the marginal distribution of x. And we're given the joint density, which is 5/16 x y squared, and we want to integrate out y to find the density of x, and y ranges from x to 2, and so then this is just a simple integration. The integral of y squared is y cubed over 3, which we get here. Limits of integration, plug it in, that's our answer. Number 4, the moment generating function for a random variable having a Poisson distribution with parameter lambda is given by this equation. If x bar is the mean of a random sample of size n from a Poisson distribution with parameter lambda, then which of the following statements is true? Number 4, we're asked to find, we're given the moment generating function of a Poisson, and then we're given the mean, and then we're asked to find which of the following are true. Well, the sum of Poissons is Poisson again, but since we're dividing by n of that sum, that confuses it a little bit. And so I'm not 100% sure what that would be exactly. But I do know that the sum of Poissons is Poisson. So if you look at answers D and E, it's probably one of those. And so the sum, or the moment generating function of the sum, is this, but this sum can be broken into the product. And since each of those are independent, we can break it up, the product of these expectations. And one of those is going to be the same, so we can just take one of it and then raise it to the nth power. But then that comes in here. And then if you look at this looks just like a Poisson distribution, except for just the parameter lambda, we have n times lambda. So that tells me that this sum is Poisson in lambda, so the answer is E. Number 5, a random sample of size 4 is taken from a normal distribution with unknown mean mu and variance sigma squared greater than 0. To test the null hypothesis that mu is 0 and the alternative hypothesis that mu is less than 0, the following test is used. Reject H naught if and only if the sum of the x1 through x4 is less than or equal to minus 20. For which of the following values of sigma is the significance level of this test chosen to be 0.14? So number 5, we are asked to find the value of theta. We're given the rejection region, that the sum is less than minus 20, and then I like to convert that to the mean, so divide both sides by 4, since we have 4 observations. So it says the mean is less than minus 5. Well, we're given that we want a significance level of 0.14, and so the probability of rejecting, and this is of course under the null hypothesis that the mean is 0. So if we subtract the mean from both sides, divide it by the standard deviation. Now remember, the standard deviation of the mean is the standard deviation divided by the square root of n, which is this piece here. And then multiply this around, you get z is less than or equal to minus 10 over sigma. Well, if you look in a standard normal curve, the probability of being less than some number equal to 0.14 is minus 1.1. So that implies minus 1.1 is equal to this, which implies that sigma is approximately 9.1. Number 6, suppose a box A contains 4 red and blue and 5 blue chips, and box B contains 6 red and 3 blue chips. A chip is chosen at random from box A and placed in box B. Finally, a chip is chosen at random from among those now in box B. What is the probability a blue chip was transferred from box A to box B, given that the chip chosen from box B is red? So number 6, we are given 2 boxes, box A and box B, and we're going to randomly pick one from box A and transfer it, and then we're going to choose one from box B. And so the question asked, what's the probability that the transferred ball is blue, given that our chosen ball was red? Now we manipulate this to get, in a case where we can actually solve it. So this conditional is the intersection of T and C divided by the probability that C is equal to R. And then this joint can be manipulated back the other way into the probability that T is B, the transferred ball is blue, times the probability that the chosen ball is red, given that we transferred a blue, and again divided by the probability C is equal to R. Well, the numerator is pretty straightforward. the probability that we transfer a blue ball is 5/9, and I have these backwards by accident. So it's probably 5/9, and the probability that we choose a red ball, given that we transferred a blue ball, is 6/10. And then we'll show that this probability of choosing a red ball is 29/45, and then this reduces to 15/29. So now once we figure out how I solve that, then we're finished. Well, that's what is down here. So the probability that we choose a red ball is, I like to do this trick on a lot of things, is I introduce another variable and then sum over or integrate over all possible cases here. So the probability that we choose a red and transferred a red ball plus the probability we chose a red and transferred a blue, this probability doesn't change. But then once we're given this, then we can transform it into this. And we're still summing over all possible values of transfer, which is just red and blue. So then we rewrite this as, and then we plug in for I our options. So the transferred ball is red, and then that's red. Transferred ball is blue, blue. And then we can just put in the probabilities. Probably we transfer a red ball is 4/9. Probably we choose a red ball given we transferred a red is 7/10. And then we get 29/45. And remember that this piece is used in the denominator to come up with that. Number 7, let y have a normal distribution with mean 1 and variance 4 and w equal to e raised to the y. Let cap phi be the standard normal cumulative distribution function. Which of the following random variables has a uniform distribution on 0 to 1? So number 7, it says which of the following random variables has a uniform distribution. And I'm going to write down the probability integral transformation. If you want more detail on this, what it says is that the CDF, or the cumulative distribution function, of a continuous random variable is distributed uniformly over 0 to 1. So if we find the CDF of W, then this is a uniform distribution. So let's look at this. But W is e to the y, and then if we take the log of both sides, we get y is less than this. But we know y is a normal distribution. So if we subtract the mean divided by the standard deviation, this is a z distribution. Well, the standard normal distribution is really, notationally, we write it like this, which says that we're being the probability of less than this number, which is this. Well, this is uniformly distributed from 0 to 1. And again, if you want a quick little proof, you can look up the probability integral transformation. Number 8, let x and y be random variables such that x has a density function of f of x equal to 3x squared. And the conditional density of y given x is g of y given x, denoted by that. Then over the appropriate domain, the conditional density of x given y is. So number 8, we're not going to be able to fit it all on here, okay? So here we're asked to find the distribution of x given y, and we can write it like this, and then rewrite the numerator like this. So we're given f of x, and we're given f of y given x, which that is this joint distribution, which is this right here. And here is our range. X is from 0 to 1, y is from 0 to 5x, which means we're in this region here. And this is going to be important when we integrate in just a second. So we have the numerator, which is this piece here. Now we need the denominator. So we need to take this joint distribution and integrate out x. So when we're integrating out x, we integrate from here to 1. Well, that, in terms of x, is y over 5. So we're going to take this joint distribution, which is here, and integrate it from y over x to 1. And we're integrating in terms of x, and so this is a constant. So we just get an x, limits of integration, plug it in, we get this. So now, to find this density, we take the information that we have now and plug it in. So there's our joint, which we found, and this is the probability, or f of y. Those cancel, leaving this, and then combine that into a fraction, you get 5 over 1 minus y. Number 9, for the regression model yi equal to b times natural log of xi plus epsilon I, epsilon equal 1 and 2. Assume that x1 is equal to e, x2 is equal to e squared, and that epsilon 1 and 2 are independent random variables with mean 0 and unknown variance sigma squared. What is the least squares estimator for b based upon x1, y1, and x2, y2? So number 9, it's asking us to find the least squares estimate of beta. Well, you do that by taking the derivative of our data minus our expected line squared, and least squares, and then we minimize this by taking the derivatives associated with b. Well, that ends up being this. The 2 comes out front, and then you subtract the 1, and then you take the derivative of the inside with respect to b, which is minus log over xy. That's the chain rule. We set it equal to 0, and now we solve for b. When we multiply this, well, first of all, I get rid of the 2, divide both sides. I divide by -1 to get rid of it. And then I take the log of x here, which is this piece, and then I take this times that, but it's negative, so I take it to the other side, and we get this. And then to solve for b, I divide by the sum of the log of xi squared and get this. Now we plug in the actual values. We're given the 2 values, which is y1 times the log of e, which plus y2 log of e squared, and that numerator becomes this. And then the bottom, this is log of e to square. This is 1, and then log of e raised to 2. This is 2, so we got 2 squared, which is 5. And that is the first part of our actuarial exam. Hope you enjoyed it. Please like it. Please subscribe so you don't miss the next portion of this, which is questions 10 through 18. Thanks. Bye.